Now you may have noticed this block here. What are they? Well, this tab on this website is not the only tab. There's a whole bunch of tabs at the top of the main page of the website. And these, you may be curious to know what these other tabs are about, these other topics. So I'll mention them briefly, just a few minutes on each one. So if you're curious, you can look at these others. Okay, so my research interests are, well, two main ones, I suppose. One is TQC, that's Topological Quantum Computing. And the other one is something I call XTEX. I'll talk about these two now. So, Topological Quantum Computing, what is that? Well, when quantum computers, QCs, when quantum computers become scalable, so when you can have large scale quantum computers, that will change everything, because theory shows, if you're interested in quantum computing, I have a large number of, well, I plan to, I'll have a large number of courses or lecture sets on quantum computing. It's a major topic for humanity for the future. A quantum computer can outperform a classical computer, today's computers, by a factor of 2 to the power n. Now, what does n stand for? Well, take a single electron, for example, and if it's spinning this way, let's say that represents a 0, and if it's spinning the other way, that represents a 1, let's say. And then have a line of these electrons, so 1, 2, 3, n. Now, connect them in a certain way, entanglement, that's entangle them, that's the technical term. If you don't know what I'm talking about, don't worry. But so you take these electrons with spins up and down, zeros or ones, and you connect them up in a certain way, and I'm being deliberately vague because it's complicated. Anyway, so you entangle all n of them, and then with that entangled n electrons up or down, they're called, each 0 or 1 is a bit. These are quantum particles, so that bit is a quantum bit, or qubit as they're called technically. You can then compute with those n qubits, entangled n qubits, you can do 2 to the n power calculations at the same time that it takes a classical computer to do one thing. So potentially a quantum computer will outperform a classical computer by a factor of 2 to the n, and that's revolutionary, because future quantum computers, if we can build them in where n is large, so have large numbers of these qubits entangled, then everything will change. Why? Because, well, I'll stick with physics for the moment and then extend later. Imagine you're a chemist, a quantum chemist, and you're using a classical, today's computer to simulate the behavior of a molecule. Now, pretty soon, you'll notice that every time you add one more atom to your molecule, the size of your problem, and in technical terms, if you know any quantum mechanics, the size of your Hilbert space doubles. Now, if you don't know any quantum mechanics, don't worry. But anyway, adding one more atom to your molecule increases the size of your problem by a factor of 2, just doubles. So very quickly, as you just keep adding a few more atoms to your molecule, your problem becomes beyond what your classical computer can simulate. It just doesn't have enough memory, it doesn't have enough processing speed and so forth. So your classical computer effectively for your problem just dies, okay? But if humanity can have quantum computers that are scalable, that you just keep increasing your n, the number of qubits, and if they can remain entangled, talk about that later, then you can keep pace, right? You add one more atom to your molecule, okay, add one more qubit to your line of qubits. Call it a register, right? That line is a quantum register. So potentially, quantum computers would allow you to simulate nature, because if you go down small enough, everything in nature is made of atoms, right? And atoms obey quantum mechanics. So the potential of quantum computers is that it could simulate nature, and if that's possible, everything changes. It would just be one of the major technological revolutions, scientific revolutions of the 21st century, because physics would be revolutionized, chemistry would be revolutionized, biology, and then technology, and then the economy, and then politics. Like, it'll have a huge impact. Now the problem is, because there's a hitch, there's a catch, the problem is that today's quantum computers, and they do exist, they've been around since 1998, right? So what's that, 14 years now? The problem is they are fragile. If you're storing information, for example, on the spin of an electron, well, any local disturbance, like some other atom or electromagnetic field, or any local disturbance, can interact with that tiny little particle, that little electron, and change its state, change its behavior. And then you lose the information. Right? That problem is called, that loss of information is called decoherence. And it's the major bugbear, the major problem for creating scalable quantum computers. All right, so late 90s, a Russian-American theoretician, mathematical physicist, a guy called Kitaev, K-I-T-A-E-V, Kitaev, he came up with the idea that, hey, maybe you could store quantum information in something called topological quantum fields. Now, I won't explain what that is, but the last decade or so, theoretical physicists, experimental physicists, have been fascinated by phenomena in physics that have weird topological properties. And I won't go into that either. But the bottom line is, if you can store information in these topological quantum fields, that information then becomes robust against noise. I'll give you one simple example of a topological property to give you a feel for what I'm talking about. Take a soft rubber donut. Right? So it sort of looks like the inner tube of a tire. So it has a hole. It has a hole in the middle and like a tire-shaped outer rim, and it just looks like a donut with a hole in the middle. And it's not made out of dough, it's made out of soft rubber. So you can squash it, you can stretch it, you can twist it. Now, if you with my marker pen, so imagine I'm holding this rubber donut, and I put dots all over the surface of that donut, and then I start drawing lines, connecting up the dots, so I get lines. It's like here's one dot and here's another and another, and I draw a line that way and a line that way. I'll then get an angle between those two lines. Okay. Now, when I deform, when I change the shape of that rubber donut, twisting and stretching and squashing it and so on, then all the traditional geometry of that surface changes, right? Like the distances between points, that all gets deformed, changed. The angles get changed. But topology, you can say, studies what remains invariant, not changing, so constant. What remains constant, even when I deform this shape, this surface? Well, common sense says, well, there's obviously one thing that doesn't change, unless I cut. So no cutting, no surgery, okay? So no cutting. There's obviously one thing that remains the same, and that's the number of holes, right? Number of holes in that surface, in that shape, okay? And in technical terms, the number of holes in a shape, a surface, is called its genus, G-E-N-U-S, genus, okay? So crudely, it's just an analogy. So if I could store information, say, like if I wanted to store the number 3, well, imagine I have one of these surfaces and I just had 3 holes, and and I squash it and deform it, well, that number of 3, 3 holes remains there, right? It doesn't change. So it's a crude analogy, but by using topological quantum fields, maybe you can store information robustly, so that if there is a local disturbance at some quantum particle system, doesn't matter, right? Because that information is stored as a topological property